In this video, we will learn how to construct confidence intervals for population means. We have already learned that p hat, the sample proportion, is the best point estimate for the population proportion p. Likewise, the sample mean x bar is the best point estimate for the population mean mu. When constructing confidence intervals using the sample mean, there are two different formulas that may be used. The first formula is used when the population standard deviation sigma is known. This formula is x bar plus or minus the critical z-score times sigma divided by the square root of n. In reality, the population standard deviation sigma is generally unknown, so we will continue on with an example when sigma is unknown. If the population standard deviation sigma is unknown, we use s in place of sigma. Remember that s is the sample standard deviation. When using the sample standard deviation s, we must now use the t-distribution instead of the normal or z-distribution. The t-distribution is symmetric and bell-shaped, just like the normal distribution, but the t-distribution is different for every sample size. In order to find a critical t-score, we need to know the degrees of freedom. The degrees of freedom is always equal to the sample size, or n, subtract 1. A critical t-score can be found using technology, or we can also use the t-table. As the sample size n increases, the t-distribution approaches the z-distribution. This is the t-table. As we notice on the left-hand side, we have the degrees of freedom, and remember degrees of freedom are equal to n minus 1, or the sample size subtract 1. As we go down the table, our sample size gets larger, or our degrees of freedom gets larger, and the numbers are found in the body of the table. These are all of our critical t-scores. The values at the top can be useful in finding your critical value depending on your level of confidence. I'll show a couple of examples. Remember that we're only going to use the t-table when sigma is unknown. So in this example, our sample size will be equal to 19, and we have 95% as our confidence level. If our confidence level is 95%, then that means that we have 2.5% in each tail on the distribution, or a total of 5% in two tails. That corresponds to the center column, where the area in one tail is 0.025, or the area in two tails combined would be 0.05, or 5%. Our degrees of freedom in this case would be 18 because our sample size was 19 and we subtract 1 from that. So we look at the row that has 18 degrees of freedom, and then the value that intersects with our level of confidence. Our critical t-score in this case would be 2.101. Let's do another example with a sample size of 8. That tells us that our degrees of freedom would be equal to 7. And so we're going to look at the row with 7 degrees of freedom, and we choose the number in that row that corresponds with 99% confidence. If we have 99% confidence, then that tells us that we have 1% that would be remaining, which means we have 0.5% in each of the tails, or, as I said, 1% in the two tails combined. That would be this first column, where we have 0.5% in one tail, or that would be 1% in two tails. So in this case, our critical t-score would be equal to 3.499. Now suppose we have a sample size of 77, and we're looking for 90% confidence. 77 is our sample size, which means our degrees of freedom would be 76. Our table does not have 76 degrees of freedom, so what we would do is use the smaller degrees of freedom, so 70. We also could use technology to find a more accurate t-score here. 90% confidence means that we would have 5% in each tail, or 10% in the combined tails. So that means we would be looking at this column for the 90% confidence level. And our critical t-score would be 1.667. Now that we know how to find critical t-scores, let's put this to work in our formula for finding a confidence interval. When sigma is unknown, and therefore we use s instead of sigma, This changes the formula slightly so that now we need to use a t-score and S in the formula. And remember that we also will need to use our degrees of freedom to find our critical t-score. Suppose we randomly sampled 27 Labrador Retrievers and found their mean weight to be 84.2 pounds with a standard deviation of 7.1 pounds. Construct a 95% confidence interval. The values that are known are X bar, the sample mean, is equal to 84.2, and the sample standard deviation is 7.1. There were 27 Labradors included in this sample, so N is equal to 27, and we're looking for 95% confidence. Because sigma is unknown, we will need to find a critical t-score, and we're going to find that critical t-score based on 26 degrees of freedom. So let's go ahead and do that. We start by looking at 26 degrees of freedom on the table. One of those 5 values there will be our critical t-score. The next number that we need is our confidence level. And so we go to the 95% confidence level, which is the one in the center. Remember, 95% confidence means that the area in either tail would be 2.5%. And that is why we are using this column that has the area in one tail at 2.5%, or if you want to think about the area in 2 tails being 5%. Our critical t-score then is 2.056, and now we're ready to input these values into our formula. So we take the sample mean of 84.2, and we add and subtract the margin of error, which is our t-score of 2.056 times S, 7.1, over the square root of N, which was 27. Now in our calculator, we will find the margin of error piece of this formula, which is just the right-hand side, and then finally we'll do the addition and subtraction piece. The margin of error came out to be 2.80931, and now we will do the addition and subtraction. I'll start by taking 84.2 and subtracting 2.80931, which is 81.391 if we round that. And then 84.2 plus 2.80931 would be 87.009 when rounded. This is an inequality, and we're expecting that the population mean mu would be somewhere in this confidence interval. We believe that with 95% confidence. In conclusion, we could say that we are 95% confident that the true mean weight of all Labrador Retrievers is between 81.391 and 87.009 pounds.